We talked about the half reactions of a redox, which we're going to look at in more detail. We talked about what reduction is, a gain of electrons, oxidation being loss of electrons. And let me go back and zoom in on this equation right here. You don't have, you should, it's already should be in your notes, so you don't have to rewrite this. But what I want to point out is something that'll help us going forward is that we always show the oxidation part happening on the right. So when something loses electrons, we show those electrons on the right side of the equation. And when something gains electrons, we show those on the left side of the equation. Another thing that we haven't really talked about, but I want to introduce before we even start talking about balance and redox equations, is the half reaction part, right? So if you notice, this is sodium going to sodium chloride, and then chlorine also being a part of that salt in the product as well. So sodium has something happen to it, chlorine has something happen to it, and then there was some step after that where you combine those two things, right? And so all of this is important when we start talking about balance and redox equations, because first of all, if you look here, the electrons on opposite sides, so we could get rid of those. And then we can just add the equations on the left together, the half equations, and the equations on the right together. So this will be considered a half equation. And this is also a half equation. But this will make more sense when we actually start balancing redox examples. All right. So let's go and talk about these oxidation numbers again. We're going to go through some examples about how to calculate those and figure out even whether oxidation or reduction even took place. So here, let me go to rule number 3, because this is very important. The other rules are self-explanatory. If you got something elemental, the charge is 0. If it's a monatomic ion, the charge is what you see. If it's a non-metal, then the hydrogen can be a proton or a hydride, depending on the situation. Oxygen normally is -2, -1 or 1/2. And then the sum of your oxidation numbers for all your atoms in the molecule is equal to the charge on that molecule, right? So let's do some examples here where we calculate oxidation numbers. And this is, again, a skill set that you're going to carry over to the next part of this section, which is dealing with redox reactions and balancing redox reactions. So we're gonna do this now. So let's talk about oxidation numbers. Today is the 28th. Can't believe this month is already gone like that. Right, so there's a way to calculate these oxidation numbers, right? And let's look at, for example, and one of the things to remember when we're doing these oxidation number calculations for different compounds is that we're going to follow those rules that we already laid out. So if we don't know the oxidation number of some element, we can solve for it. That's the bottom line. So let's take it, for example, we're going to calculate the oxidation number for, in this one example, for sulfur. So we have a compound like H2S, right? If you notice, when we're talking about oxidation numbers, we're talking about this compound and the 2 atoms that make it up. All right. Now, let me show you a way to think about this. If let's say, for instance, this was an ionic salt, right? How would you, if we put this together using a crisscross method, what would it look like? Anybody, if we did it doing the crisscross method? Where did that 2 come from? And what is the subscript for sulfur?
subscript for sulfur would be 1,
Okay.
and it's just too hydrogen.
You cutting out, but I hear you. And I think what you're saying is if I undid this, it would look like this: H plus 1 and then S minus 2. Is that right?
Yes.
Because if I crisscrossed them, the 2 would go here and the 1 would go here. But this is not always possible. So we can also calculate the oxidation number, right? So let's do that. So the overall molecule itself, the charge is neutral. So whatever we do, we're going to set it equal to 0. So all your oxidation numbers have to add together to give you 0. So we're going to take this and we're going to say 0, which is the charge, the overall charge. And we're going to say, now based on the rules, hydrogen we know is either going to be +1 or -1. But since we know that sulfur, based on its periodic table location, is going to be negative, we don't know. Now we know it's -2, but I'm showing you how you can solve to prove that it's -2. We know it's going to have a negative charge. So in this case, we're going to say that, and really, hydrogen is only -1 or negative when it's attached to a metal. Sulfur is not a metal. Sulfur is a non-metal. So we know hydrogen is going to be +1 in this case. So we're going to say that this is, for hydrogen, 2 times +1. It's important to keep that charge in there, right? And it's going to be plus X, right? We don't know what sulfur is. And this is for sulfur. But we can solve for it, right? So that's going to be 0 equals 2 plus X. Is that right? So this is the oxidation number. Let me make sure we clear on everything that's being represented here. This is the oxidation number for hydrogen, and this is the oxidation number for sulfur. Let me clean that up a little bit. Get a little thinner pen. All right. So now we can just solve for X. So 0 minus is going to be what? 0 minus 2. Is that right? If we just get X by itself.
Yes.
0 minus 2 equals X. So minus 2 equals X. So the oxidation number for sulfur is -2. That's how we solve for that. If we know one, we can solve for the other one. And that's why we need those rules so we can know how to set this up. The first rule, the last rule says that the sum of all your oxidation numbers is equal to the charge on the molecule. And so the charge for H2S is 0. So that's the overall charge. I didn't even realize I didn't finish that word out. All right, that's the overall charge that we set everything equal to. We know hydrogen with a non-metal is going to be +1, and there are 2 of them. So we got to put that number in there, times +1, which is the oxidation number. And then we're going to solve for X. All of these problems that we're going to look at with these oxidation numbers are the same way. So let's do another example. Are there any questions about that? Let's do another example. All right. So the oxidation number on sulfur in this case is -2. All right. Let's do another example where we have a compound with more than 2 atoms. It's going to be KNO3. Can somebody tell me what the name of this compound is?
Potassium nitrate.
Potassium nitrate. Excellent. So what's the overall charge here?
0.
It's 0. Overall charge is zero. There's no positives or negatives. Everything is balanced. So the overall charge is zero. So we want to set, and now we want to know what the oxidation number is for nitrogen, right? So if we broke this apart, this would be K plus and then NO3 minus, all right? So K plus falls into the class and rule 1 or rule 2 about a monatomic ion, right? So we know that this is a monatomic ion. Right, but because it's there in the salt, we got to keep it all together. We can't just take in, well, we could solve NO3, but we're going to do it this way. All right. So this is going to have a oxidation number of +1. And then we know oxygen, if it's involved in a molecule and not molecular oxygen like O2, the charge is the oxidation number based on the rules is -2. Right. So now we can solve this. We can take the whole thing. We got the two numbers that we know we took from the rules. Right. So now we can take what we know and solve for what we don't know. So the overall charge is 0. We're going to set that equal to, we got 1 potassium. So 1 times the oxidation number of +1. We know that's going to be 1. I know it's simple and elementary, but it's a process. That's what I'm concerned with, the process. Right. We got 1 nitrogen. So this is going to be 1x. And then we got 3 oxygen. So that's going to be 3 times -2. Following? Anybody not following? So all this little math, this little bootleg math that you learned in the 3rd grade is coming back now to help us figure out oxidation numbers. Okay, let me change this X because I don't want you to think that that is an XX. So I'm going to just say, I'm going to make it bigger. So 1 times +1. And this X is for, and this is potassium, this is oxygen, and we're going to solve for nitrogen. So now 0 equals 1 plus X minus 6. Any questions about that? All right, we can combine these terms right here. So that's going to be -5 plus X equals 0. And so now we can just solve for X. So 0 plus 5 equals X. X equals 5 plus 5. Make sure we say that because the oxidation number can be positive or negative. So the nitrogen, the oxidation number for nitrogen is +5. Very important. Very important because that number on any given atom is going to tell you whether or not, when you compare it to itself on the left side or the right side of a reaction arrow, that number, being able to calculate that number is going to tell you whether or not that atom got oxidized or reduced. All right, so it's a very important skill to have, and I know it seems tedious, but it's an important skill to have. All right, let's do one more, and then we're going to look at how to apply this to an actual redox reaction to tell what got oxidized and what got reduced. So let's do one more example. Any questions? Everybody good so far? All right, let's do one more. So let's take H2PO4 minus, and we want to solve for P, phosphorus. Come on, Albert. We're gonna solve for phosphorus. What do we know from the rules about H and O already? If oxygen is involved as an atom in a polyatomic or an atom bonded to some other atom, what's the oxidation state for it, or the oxidation number? What was it over here? Right, oxygen is always -2 if it's just bonded to another atom. If it is by itself as a molecule of oxygen, O2 is -1. If it's with fluorine, it's 1/2. All right. So we're gonna break this down. We know that hydrogen, based on the rules, hydrogen is +1, oxygen equals -2. We know that, and we can solve for P. Now you can take this somehow and take the PO4 and solve for it that way, but we're not going to do that. We're going to keep it all, everything together and solve it all at once. All right. So what's the overall charge that we're going to set everything equal to?
-1.
-1. Excellent. The overall charge, that's important. Once we know that, we set everything equal to that number and solve for the unknown. Right. So here, -1 is the overall charge. Excellent, excellent, excellent. And then we'll set that equal to, how many hydrogens do we have? Because we got to keep the numbers consistent. So it's going to be 2 times +1. Because we know the oxidation number on hydrogen, if it's in a bond with a non-metal, is +1. Right. And then for oxygen, it's going to be what? 4 times what? -2. Is that right? Because we're using the rules to our advantage. Some of the stuff we already know without having to look it up. We know oxygen is -2 if it's bonded to some other atom besides itself. Right, so it's -2. H is +1 if it's bonded to a non-metal. So now we just need to solve for P. How many P's do we have? Now keep in mind that P here, this 4 is not distributed, okay? Because I know that might be a trap or a snare when you see that 4 outside of the oxygen to distribute it, because that's what we've been learning. But the only time that number will be distributed is if there's a number here, and we don't have one. It's understood that there's one PO4, so that means that there's only going to be one P. Are y'all following that? Did y'all catch what I was saying there? So don't distribute that 4. Right, so we're going to do that, and then this is plus X. I'm not even going to put the 1 in front of it. The 1 is understood. All right, so let's just go ahead and do this little math right here. That's 2 minus 8. Is that right?
Looks right to me.
Plus X. Is that right? Equals -1. Yes, no, maybe. All right, so we'll do this little math. So that's -6 plus X equals -1. And we just solve this. Plus 6 is X. So +5 equals X. I want you to notice something, because one of the things about doing chemistry is the ability to notice and recognize trends. Where is P in the periodic table? Where's phosphorus? Anybody?
Isn't it like towards, it's not directly on the right side, but it's like
It's on the right.
generally right side of periodic table.
Where is it? Where exactly is it? Is it under carbon? Is it under nitrogen? Is it under oxygen? Is it under fluorine? That's the question. Because that's where we start for non-metals, right? Boron is a metalloid, And then there's that zigzag line on the periodic table. And then it's carbon, nitrogen, oxygen, and then the halogens. So phosphorus is underneath the nitrogen. Following?
Yes.
So that number is plus the oxidation number for phosphorus in this case is +5. What did we get for nitrogen up here when we solved for it? It was +5, wasn't it? Right. So if they're in the same group, a lot of times the oxidation numbers are going to be the same because those elements act the same way. Right. They do the same things a lot of times. So I just want to point that out, that trend out. So now we can expand our definition on reduction and oxidation. We talked about reduction and oxidation, meaning the loss or gain of electrons, but now we can say in a redox reaction that one or more of the elements involved is going to undergo a change in oxidation number. All right, so one or more of the elements involved is going to undergo a change in oxidation number. That's really important. And the fact that if we're able to calculate oxidation numbers, what that means is that we'll know exactly which one underwent oxidation, which one underwent reduction. Because if your oxidation number goes down, that means you've been reduced. If your oxidation number goes up, that means you've been oxidized. Are y'all following? So when we say change in oxidation number, if the oxidation number increased, that means oxidation happened. All right. If the oxidation number decreases, I'll fix this before I post it. That means reduction happened. All right. Very important. Very important to understand that concept. All right. Oh, are we okay? Now we have some different meanings for oxidation and reduction. We said loss of electrons, gain of electrons. Now we can say increase in oxidation number or decrease in oxidation number. All right. Questions? Any questions? All right, let's look at some examples of how to detect whether or not a reaction is a redox reaction. So let me put another heading here. So let's talk about that. Let's talk about how to determine if a reaction is indeed a redox reaction. So I'm going to go through a few examples and then introduce you to how to balance redox reactions. It's a very tedious process, but it's doable. It's not impossible. All right. So we're not worried about what's possible and what's not possible. We can do anything we put our minds to. All right. So let me give you some examples of how to determine whether or not an oxidation or reduction actually took place. All right. So let me give you this example first. We're not going to calculate oxidation numbers for this example. We're actually just going to look and evaluate it. All right. So we got zinc metal right? And we know that if it's elemental, the charge is 0. It's not an ion. So we got zinc metal, and we're going to react that with, let me put it over here. We're going to react that with HCl. And we're going to make this over here, zinc chloride plus hydrogen gas. And you actually saw this, right? When we did the acids and bases lab, I think Jan added some HCl to zinc metal, and you saw some bubbles and some gas evolution. So that's a real reaction that you can do, right? If you look at that, let's just take the zinc, for instance. Look at the zinc here. This is zinc 0. What's the oxidation number on zinc over here? Without calculating it. Think back to when we were doing nomenclature and building compounds from 2 ions. What is if we wrote that zinc chloride in ionic form, what would it look like? All right, so let's undo it. Let's pull it apart.
Oh, it would have a 2+ charge.
Come on with the come on. Come on with the come on. This is zinc 2+, and then Cl what? -1. Is that right?
Yeah.
So what is the oxidation state or number of zinc in the products? It's the number, it's the charge, right?
Yeah, 2.
So it's 2+. What is it in the star material or in the reactants?
0.
0. So did zinc get oxidized in this case?
Yes.
It did. It did. Good. That's what I'm trying to point out. So zinc. All right, zinc got oxidized. Now let me say this as a caveat. Whenever oxidation, if it's a redox reaction, when oxidation happens, by default, reduction happens. All right. So you can't have one without the other if it's a redox reaction. So what is the charge on chlorine right here?
-1.
It's -1, right? And then hydrogen is +1. So over here, right, we can see that the chlorine will be -1. And on the other side is also -1, but there are 2 chlorines, right? And so we can say that the chlorine is what is going to be reduced in this case. So if zinc got oxidized, we can say that the chlorine gets reduced. Or we look at the hydrogen. What is the charge on hydrogen? Over here is +1. And then over here is elemental. So it's 0, right? So the hydrogen gets reduced in this case, not the chlorine. I apologize for that. Chlorine is -1 on both sides. It's the hydrogen that actually got reduced because it went from +1 to 0. So zinc got oxidized, and then hydrogen gets reduced. This has to be, it's a concurrent process, right? Or concomitant process. When oxidation happens, so does reduction. So hydrogen is reduced. Chlorine has the same charge on both sides. It's -1. And when we balance this out, right, which we didn't do, but we can balance it now. I should have done that first. You put a 2 here, and then the hydrogens balanced and the chlorines are balanced. So it's hydrogen that gets reduced, zinc that gets oxidized, right? So anytime you have, if it's a redox reaction, anytime you have reduction, you're also going to have oxidation. Anytime you have oxidation, you're always going to have reduction. All right. So let's look at one more example like this before we go into determining whether, like here, I'm just showing you what's happening on either side of the arrow. But in the other examples that we do, we're going to check the oxidation numbers to see what happened and what got oxidized and what got reduced. So let's look at it. One more example. So if I take copper, elemental copper, plus silver nitrate, and that gives me copper nitrate plus elemental silver. All right, let's balance this real quick and then we can figure the rest of it out. So how would you balance that? What do I need to balance? Can I keep my polyatomics together and just look at it that way? This is actually a one of the reactions that we're going to do. It's just iron sulfate and copper instead of silver nitrate and copper. But you actually can precipitate out one metal by swapping it with the other. So it's like what we call a single displacement. Anybody? What if I put a 2 here? Would that balance out the? If I put a 2 here, would that balance out the nitrates?
Yes, but you have to put a 2 in front of the silver.
Come on with it. Come on with it. That's what I was hoping for the follow up to that. Excellent. All right. So now let's look at copper. Copper is elemental. So that means it's 0. So this is copper 0. Over here, if we pull that apart and undid it, what would the charge be on copper? And what would the charge be on the nitrate?
+2 and nitrate would be -1.
Excellent. So this is Cu plus 2. Do you see why when we were doing the other reactions, when we talk about writing it in ionic form, that's why. Because we need to know what the ions look like and what the charges are. That's important. What happened to copper? Do you see what happened? It went from copper 0 to copper plus 2. So if the oxidation number went up, did it get oxidized or reduced? If the oxidation number increases,
It oxidized.
got oxidized. Right? Now let's take silver, for instance. Silver on this side, if we undid this, it would be what? Ag plus 1, NO3 minus 1. Is that right? We know the charge on NO3, that doesn't change. That's a polyatomic that we've already learned. So the nitrate is always going to be -1. So Ag in this case is plus 1. Is that right? And we got 2 here, 2 here, and over here, we're going to put this 2 here, right? Because we got to keep that consistent. And then what about the silver on the other side? We got 2 what? What's the charge on silver over here? It's elemental, so it's going to be what? 0. So what happened to silver? The charge went from what? +1 to 0. Did that get oxidized or reduced?
Reduced.
It got reduced. So again, anytime you have a redox reaction, something is going to get oxidized, something is going to get reduced. And let me connect the two ideas about increasing or decreasing oxidation number and the original idea of gaining or losing electrons. So the copper, because it got oxidized, it lost electrons, right? How many electrons did copper lose to go from 0 to 2+? If each electron has a -1 charge. So you go from 0 to +2. How many electrons would you have to lose in order for that to happen? Well, if I went from 0 to +1, how many would I have to lose?
1,
1. So if I go from 0 to +2, how many do I have to lose?
2,
All right, if I go from 0 to +5, how many would I have to lose?
5,
5. Every electron has a -1 charge. So this lost 2 electrons, right? And by the same token, the silver that got reduced, right? It did what? It went from 2 silver +1 ion cations to 2 silver 0 elemental particles, right? So this what? It got reduced, so that means it gained 2 electrons, right? So each one of those +1 silver ions gained an electron. Are y'all following that? Is that making sense or no? Because this is all these little things that we're talking about now, you're going to see them again when we're balancing these redox equations, which we'll do on Wednesday, more than likely. All right, no questions. Everybody good? All right, so good. So let me give you an example, 2 examples, and we're gonna stop. I'm gonna give you one reaction, and we're gonna determine if it's reduction or oxidation happened. And we want another reaction, we're gonna do the same thing. So let's do it. Let me just put it on another sheet of paper. All right. So let's see if we can do this. So I'm just going to ask the question, did redox occur? Right. So the equation is zinc carbonate, which is insoluble. So zinc carbonate goes to zinc oxide plus CO2. The question is this a redox reaction? All right. The way we find that out is to think about the oxidation numbers, right? In this case, because we know the zinc carbonate salt, we can pull it apart. If we pulled it apart, what would it look like? What's the charge on carbonate? Anybody remember that? Let me put some incentive on the line, put lunch on the line. What's the charge on a carbonate anion? This is a salt, so we can pull it apart. So this is going to be zinc and then CO3. It does have a charge now. And it's already balanced, so we don't worry about that part. Anybody? Going once, going twice. I'll buy myself lunch. It's -2. So that means that zinc is, again, those polyatomics, you gotta have a firm command of those, because that'll help you save you some time in certain situations where you don't have to where you won't have to actually go in and say, oh, let me calculate this or let me calculate that. You don't have to worry about that. If you know the charges on your polyatomics, you can rip these salts apart and get an idea of what happened. All right. Over here, what's the charge on oxygen based on the rules that we just went over? Anybody remember? Oxygen, when it's bound up with another atom that's not itself?
-2.
-2. Excellent. So if we pull this apart, we'll get what? O is -2 by default. So this has, and there are no subscripts. So this has to be what? +2. What happened to zinc? Did anything happen to zinc?
No.
It's +2 on this side. It's +2 on this side. So no, this is not a redox reaction because zinc stayed. Well, let me not say stayed. Zinc kept the same oxidation number. Zinc kept the same oxidation number. So zinc didn't change. All right. Everybody, we're okay with that? If the oxidation numbers don't change, that means that nothing happened. The reaction happened, but it wasn't a redox reaction. It might have been some other type of reaction, but it wasn't redox. All right. Let's do one more and we got to stop. So let me give you this one. So this is, let's see, gallium plus Br2 this is gallium tribromide. All right, and let's balance this. Are the atoms, is the equation balanced as we look at it, as it stands? Got 3 bromines on one side and 2 on the other. That's not balanced, is it? So we're gonna balance this by, if we put a 2 here, is that right? That'll make it 6 bromines and 2 galliums. And then if I want to, I need to balance the bromines out. I can put a 3 here. That'll be 6 bromines on this side. And then I can just put a 2 here. And that's 2 galliums on that side. Following? Yes, no, maybe.
Yes.
All right. So let's do this one. We're going to do it both ways just to prove the point. So gallium as an element, according to the first rule of oxidation, or the second rule, first rule, elemental things that are elemental substances, the charge is 0. So gallium here is 0. All right. And then over here, can we rip this apart? It's a salt. We can rip it apart and undo it and reverse our crisscrosses, right? And we can break this apart into what? Gallium and bromine. And what is the charge on gallium based on that subscript?
+3.
+3. Excellent. And then that makes this what? -1. Is that right?
Yes.
All right. And then over here, so what happened to gallium? Gallium went from what? 0 to what? +3. Is that right?
Yes. So wouldn't it mean it would be oxidized?
Not oxidized. How many electrons did it lose?
3.
It lost 3 electrons. Good. It lost 3 electrons. All right. And then by the same token, bromine is elemental also, and it's 0. The charge is 0. But on the other side of the arrow, bromine's charge is what? I need another color because that's going to look crappy. What's the charge on bromine now?
-1.
-1. Right. And if you worried about the numbers, this 2 would distribute. So that'll be 6 of those over here. And this 3 is going to distribute. So you got 6 of them over here. So it is balanced. All right. So the every bromine is -1. Right. But if we just take one of them that went from 0 to -1, what happened to that element? Did it get reduced or oxidized? Keep in mind, we're going from 0 to negative. That's going down, right? That's not going up. So bromine, if gallium got oxidized, bromine got what? It got reduced, right? And it lost or gained, it gained 6 electrons, right? And the gallium, since there were 2 and each gallium lost 3 electrons, right? We could say that it lost a total of 6 because the electrons got to be the same on both sides. Right, so it actually lost you're gaining and losing. Your gains and losses are going to have to be equivalent, right? There's a step in the balancing of a redox reaction where you actually have to go in and balance the electrons if they're not the same, but that's different. This is a different case. All right, let me ask this and we got to go. If I know that Br, if I know that the charge on the total charge is 0, and I know that Br has an oxidation number of -1 because it's a halogen, and there are 3 of them. Actually, there's 6 of them because that coefficient means that there's 6. And then this is going to be plus X. Is that right? Well, actually plus 2X because there's a 2 in front of gallium. I could do this the other way that we looked at as well, right? So this is going to be 0 equals -6 plus 2X. We're going to, so 6 equals 2X, X equals plus 3. So we could solve it either way. We could tear it apart. That's the shortcut method. But we can also go back and look at that gallium and say, oh, we can do it this way because the gallium tribromide, the overall charge is 0. I know from the rules that group 7 halogens are all -1. And I know from here, I got 6 of them because I have a 2 here and a subscript 3 here. So that's 6 total, right? So I can solve for X and then still find that gallium is plus 3. So I can prove it both ways. So we know this is a redox reaction. Right? One thing got oxidized, one thing got reduced. All right, we got to stop. I went way over time. So we're going to stop here and we'll pick it up on Wednesday